Good morning everyone, this is Ken Jasperby and today I am going to discuss to you the chapter 5, the second law of thermodynamics. Under this chapter, I'm going to explain the heat engine and thermal efficiency, heat pump, refrigerator, and coefficient of performance. A heat engine is a system that transfers thermal energy to do mechanical or electrical work. The thermal efficiency of a heat engine is the percentage of heat energy that is transformed into work. Heat pumps, air conditioners, and refrigerator utilize heat transfer from cold to hot. They are heat engines run backward. We say backward rather than reverse because except for Carnot engines, all heat engines, though they can be run backward, cannot truly be reversed. So let's proceed to heat engines and thermal efficiency. Heat engines turn heat into work. The thermal efficiency expresses the fraction of heat that becomes useful work. The thermal efficiency is represented by the symbol N and can be calculated using the equation, where W is the useful work and the QH is the total heat energy input from the hot. Heat engines often operate at around 30% to 50% efficiency due to practical limitations. It is impossible for heat engines to achieve 100% thermal efficiency according to the second law of thermodynamics. It is impossible because some waste heat is always produced in heat engine. Heat transfer occurs spontaneously from a hot object to a cold one, consistent with the second law of thermodynamics. A heat engine, represented here by a circle, uses part of the heat transfer to do work. The cold and hot objects are called the hot and cold reservoirs. QH is the heat transfer out of the hot reservoir, W is the work output, and the QC is the heat transfer into the cold reservoir. So now let's proceed to heat pump, refrigerator, and coefficient of performance to be reported by Ms. Remperas. But first, let us define the heat pump. A heat pump used to warm a home must employ a cycle that produces a work fluid at temperatures greater than typical indoor temperature so that heat transfer to the inside can take place. Similarly, it must produce a working fluid at temperature that are colder than the outer temperature so that heat transfer occurs from outside. The basic components of a heat pump in its heating mode shown in figures. A working fluid such as non-CFC refrigerant is used. In the outdoor coils, the evaporator, heat transfers QC occurs to the working fluid from the cold outdoor air, turning it into a gas. A simple heat pump has four basic components: condenser, expansion valve, evaporator, and compressor. In the heating mode, heat transfer occurs to the working fluid in the evaporator from the colder outdoor air, turning it into a gas. The electrically driven compressor increases the temperature and pressure of the gas and forces it into the condenser coils inside the heated space. Because the temperature of the gas is higher than the temperature in the room, heat transfer from the gas to the room occurs as the gas condenses to a liquid. The working fluid is then cooled as the flows back through an expansion valve to the outdoor evaporator coils. The formula COPHP is equals to QH over W, represented the coefficient of performance COPHP of a heat pump, where QH is the heat transferred to the warm space and W is the work input required. Essentially, it's the ratio of the desired heating effect to the energy input needed to achieve it. The purpose of a heat pump is to pump some heat from outside and from the work done on the pump to pump a larger quantity of heat into the room, large enough indeed to warm the room appreciably, supposing that you don't keep all the windows wide open. Second is the refrigerator. A refrigerator does the opposite. It absorbs heat from a cold reservoir, like the inside of a refrigerator. Uses work, usually from electricity, to transfer this heat to a hot reservoir, like the air outside. The purpose of a refrigerator or fridge is to pump some heat, Q1, from the food, or whatever is to be kept cool. The quantity Q1 is the refrigerating effect during the operation of a fridge. A somewhat greater quantity Q2 of heat is expelled into the room, though this should not result in a very noticeable rise in temperature of the room, partly because the room has a large thermal capacity, and partly because much of this heat will be lost through the windows. The coefficient of performance of the fridge is the refrigerating effect per cycle, Q1 divided by the net work done on the fridge per cycle, and for a Carnot cycle, it can be calculated from T1 over T2 minus T1. The idea that there are things called heat engines, refrigerators, and heat pump, which are represented by Carnot cycles or similar cycles, with arrows going in different direction, a few equations with different subscripts and subtly different definitions of efficiency or coefficient of performance.